Hello everyone, thank you for coming today. I'm pleased to introduce Jonathan, who is a postdoc at LSE studying the economic impacts of points. And we're going to tell you all about today. So,
lovely to see everyone. Lovely to see everyone online as well. Do shout if you lose sound or anything at any point. Yeah, so as heard, I'm working on the economics of climate tipping points with David Stainforth at LSE. So I'll give you a general idea of kind of the key takeaways and the concepts that I'll be talking through today. So I'll talk a little bit about what climate tipping points are, which may be familiar to many of you, as well as how we understand some of the uncertainty around them and some research that I've done around characterizing that uncertainty. I'll then talk a bit about how we take that physical information, that physical uncertainty, through to the economic damage assessments and how that's pulled through and how that ends up in economic damages. And then I will talk about the work we're trying to do currently to actually pull that uncertainty through more. So often these analyses only take through the mean from your multi-model ensemble or something, and they ignore the range of uncertainty we have about the future climate state. And so that's one of the things we're working on at the moment. And so I'll kind of round off with some more discussion of that. So a good starting point, I suppose, is what actually is a tipping point. So I think a good definition of a tipping point is a qualitative change of state once we go past a threshold. So in the example here, I think you can see my mouse, but on the left-hand side, if we push the ball up the slope, it will roll further up the slope and it will push back onto us harder and we'll reach a new stable point. If we let go of the ball, it will roll back towards us. But once we go past the top of the hill, if we push the ball a bit more, it will start to roll away from us. That's a very different type of behaviour as you kind of go past that threshold. So on one side, it rolls back towards us. On one side, it kind of accelerates away past that threshold, that kind of tipping point, with a very different behaviour. And we know that these tipping points do exist in the real world. There are a number of different systems that show these tipping points. A fairly trivial example is things like coral reefs, where we know once you go past a certain temperature threshold, we see coral bleaching and the algae and parts of it that create the nutrients are ejected from the corals. And even if we reduce the temperature back down again, it's very hard for those corals to recover. So we kind of cross that threshold. And an even more trivial example, again, a lot of these tipping points are very clear from biological systems, which have these very non-linear behaviors, are extinction events. Once you drive an animal to extinction, even if you restore its habitat, try and make the area more friendly towards it, the animal doesn't come back. The animal's still extinct. It's basically impossible so far to bring them back. So very strong thresholds there. And we think that tipping points may exist in the future Earth system as well. So this is a great paper that I'm sure that many people here are very aware of, by David Armstrong Mackay, looking at the different tipping points that might exist in the climate system. And it's not critical that you read through or understand all of these individual ones. Two that I'll talk about a bit more to give you a general sense of these tipping points, and I'll refer to throughout the talk, are the Greenland ice sheets and the Atlantic Meridional overturning circulation, which I'll discuss more in a little bit. But it's important to note that this is by no means saying that all of these will occur, or saying that this is a comprehensive list of tipping points. I'm sure most people think of many other examples around extinction of other animals, or just other examples of similar climate tipping points. So this is not an exhaustive list by any means. So to give you context what these kind of look like, one of the main ones are these Greenland West Antarctic ice sheets, which have instability feedbacks whereby once we start melting them a bit, they will continue to melt more and more, or we think they may. So for example, one of the main ones of those is the marine ice sheet instability, it's Missy up here, whereby the rate at which the ice sheet flows, the rate at which it melts and kind of goes into the ocean, is dictated strongly by the thickness of the ice sheet at this grounding line, where it meets the ocean. And as it melts, if it has this kind of slope that slopes away from the ocean, so it gets deeper as it goes towards the center of the ice sheet, then the front of this ice sheet gets thicker as it melts. It gets this, this line gets longer. The height of the ice sheet where it reaches the water is greater, and so it flows faster. And so as we melt the ice sheet back, the ice sheet flows faster and melts more quickly. So you get this positive feedback loop of progressively more and more melting. And there are other instabilities that we see in some of the polar ice sheets. I won't go into all of them, but it's these instabilities that can lead to tipping behaviours in these ice sheets and similar. It's also important to understand why we care about these points. So with the polar ice sheets, one of the main impacts they have is sea level rise. So we can see here, if we melted all of the Alaskan glaciers and all of the polar glaciers, we might be seeing perhaps 0.7 meters of sea level rise. And perhaps you might want to think about how much it is more. Sea level rise we would see if we melted Greenland or the Antarctic ice sheets. And it's a lot more. So with Greenland, it's a factor of 10 more. We see 6 meters of sea level rise if you melted all of the Greenland ice sheet. And then with Antarctica, it's even more. It's basically another factor of 10. So yeah, 70 meters of sea level rise if we melted all of Antarctica. So these are really big numbers that we could be locking in with these tipping points. It's important to note that we're not suggesting this is going to happen immediately. So tipping points have different timescales, and the ice sheets would take a long time to melt and pass, and to melt completely. These are kind of the estimated levels of sea level rise out to 2100 from a range of climate models. So, most of these models are predicting up to a meter or two of sea level rise by 2100, depending on which one you take. But it's important to also note that in the most recent update, they had this fun little dotted line on the top, which is basically saying, well, what if the models are missing something or are wrong? So it's really quite possible the models are slightly overconfident about their range down here. So maybe a few meters of sea level rise is not implausible, but certainly no one's suggesting that the entire Antarctic ice sheet is gonna all collapse in one go. These tipping points can also have links onto other tipping points. So for example, the Atlantic meridional overturning circulation is strongly influenced by the ice sheet melt. So this circulation is the circulation in the Atlantic here, which brings warm water at the surface north towards Europe, and then sends colder, dense water back south down the middle of the Atlantic. You may recognize this section here as the Gulf Stream bringing warm water across from the Gulf of Mexico over to warm Europe. And a key part of this circulation is that dense water forms around Greenland, Iceland, Norway, and around Canada, because it gets colder and saltier. And as that dense water forms, it sinks. And it's a bit like if you imagine you're in a supermarket and there's a conveyor belt and you're pulling the conveyor belt towards you to kind of pull it around. This dense water sinking acts to pull the rest of the current around. It pulls that warm water northward and kind of keeps the whole circulation going. And with greater freshwater release and greater meltwater coming from Greenland and the glaciers in the Northern Hemisphere, that makes this surface water lighter. It makes it harder for it to sink, basically making it harder for you to kind of pull this conveyor belt around, making it more difficult for this current to keep flowing, which is theorized to potentially lead to this circulation shutting down. So this is one way in which one element tipping can lead to changes in another element. And if this circulation was to shut down, it could potentially have some quite significant impacts on at least Northern Europe and America. So this is the one estimate of the temperature changes we might see with 5, 6, 7, 8 degrees of cooling over areas of Northern Europe, and similar over America and Greenland, with some warming in the Southern Hemisphere. And I tried to find an example to put this into context of what this would mean. So this is Cambridge, this is where I live, very sunny, one of the driest places in the UK, nice summer days with the grass and the punting. Quite cold winters, it's been pretty grim recently, not much fun. But, overall really quite pleasant. I tried to find somewhere that was, around 5 degrees cooler, similar to what we'd see in AMOC shutdown. And I had to go quite a long way. I ended up going all the way up to Iceland and Reykjavik, which, is about 5 degrees cooler over the course of the year, some months less, some months more. And as you can see, there's a lot more snow and a lot less agriculture. And you can really see how this will have a huge impact on UK agriculture and also on infrastructure. We know how well the trains and the roads and the planes in the UK cope with even small amounts of snow. So with changes like this, it would have a really big impact on lots of how we go about our lives. So these tipping points could have really potentially large consequences for human society. And you might hope that given these large consequences all around the globe, that we have a good idea of how hard they are to tip, how long they might take to tip, and all of their dynamics. But actually, as you can see here, we know less than you might think. So the x-axis here is a load of different climate tipping points. So you don't need to read all of them or understand what they all are. The important, but you'll recognize some of them, like the Greenland ice sheet or the Atlantic overturning circulation I've been talking about. The important thing to really focus on is this y-axis, which is the global warming from pre-industrial, so before we started emitting greenhouse gases, and the fact that, and each of these bars represents the range in which we think this element might tip. So the bottom of the bar represents the lowest temperature we think might be necessary to tip this element, and the top of the bar represents the temperature beyond which we think it's very likely this element will have tipped by that point. This is taken from, again, the same review paper as before. And you'll notice that actually a lot of these bars intersect with the range of like 1 to 4 degrees of warming, the kind of plausible range we might see over the next 100 years. A lot of these bars intersect with that. So a lot of these are plausibly relevant in the next 100 years. We might be entering into these ranges. You'll also hopefully notice that these are really big bars. For the Greenland ice sheet, there's an uncertainty of perhaps we've already passed the tipping point and we've already triggered some of this melting, and perhaps we won't cross that threshold until 3 degrees, which is a huge difference for human society, knowing how much we're able to overshoot, how close we are to this range. And for things like the overturning circulation, there's a whole range from about 1.5 to 8 degrees, which is, again, huge and makes it incredibly difficult for us to plan around. So reducing and understanding this uncertainty as well as we can is really critical. So one of the things that we're working on doing at the moment at LSE is to try and characterize this uncertainty that we have across the scientific community. And we're doing this in a number of ways. One of the key ways is through expert elicitation. So this is a paper which did similar work about 18 years ago, looking at an expert elicitation of what experts in the Atlantic circulation thought could happen over the next 500 years with either a doubling or a quadrupling of CO2. And what you'll notice is there's a lot of lines, and they don't all go in the same directions, they don't all go in the same places, and they don't even end up in the same places. There's a lot of disagreement. And it's a really good illustration of how much uncertainty we have about what this system might do, how much forcing might be required to make it collapse. You can see at 2 degrees, most people, 2 times CO2, most people think that it will recover, but some don't. while at four times CO2, many think that a collapse is much more plausible. So we're hoping to extend this analysis partly to understand more from a possibilistic point of view, what scientists think is plausible. So do we think a collapse this century is plausible? Do we think a strengthening of the AMOC is plausible? What timescales are we looking at? How much do we think it's able to reduce by? Because these are big questions that scientists don't necessarily all agree on. And we're also hoping to dig into the narratives and the key mechanisms. So if we did see a collapse in this century, what would have to happen? What would be the things you expect to see for that to happen? If it's very unlikely, what are the unlikely steps? And likewise, what would you expect to see for a recovery? What would you need to see different to a collapse? So that we can understand where scientists differ in their opinions and where there are key uncertainties that we can try and understand further. So this is maybe a good time to discuss some work that I've done previously. So I mentioned earlier that sometimes these tipping points can influence each other, and sometimes one tipping point can cross a threshold which can force another over the threshold. So the kind of classic example is of the Greenland ice sheet releasing fresh water, which then helps to push the Atlantic circulation over a threshold. And this can act kind of like dominoes in a domino run, where you tip one over and then it kind of pushes others over the edge. We get this kind of cascade. And so over the last couple of years, I was working with Nico Wunderling on this network model of climate tipping points they've developed, where we have a range of climate tipping points, each of these nodes here, so the ice sheets and the overturning circulation that I've spoken about already. And each of these is represented as a very simple one-dimensional differential equation, which is able to tip and has an on and off state. And these are forced both by a kind of global warming level, which can help them cross these thresholds, but also by their interactions with each other. So there are these destabilizing links, these red arrows. So this might represent, in this case, for example, the Greenland ice sheet releasing fresh water when it tips and helping to tip the AMOC. But there are also the stabilizing effects. So I showed that if we collapse the Atlantic circulation, that cools down the northern hemisphere a lot, which helps to stabilize the Greenland ice sheet because it's colder, so it's less likely to melt. And so we've got this whole network of different tipping points based on research available at the time from these reviews of tipping points. And for each of these interactions, we have a range of plausible strengths that we've taken from literature. And for each of these tipping points, we've given them a temperature threshold beyond which they tip and a time scale that takes, again, taken from this literature. So really what we've done is for the temperature threshold, we've randomly selected from within these bars, treated them as uniform distributions, and done very similar things for the time scales and the interaction strengths. And once we've done that, we've done some statistical analysis called soul ball analysis, where we aim to understand which of those uncertainties has the biggest impact on what the system ends up doing. So how many elements end up tipping? What state does the system end up in? And what you see is that the elements with the largest impact, which we colored in red here, are the temperature thresholds of the ice sheet. So we have the links in their colors. We have, if it's the time scale, it's the clock in the middle of the element. And the temperature threshold is represented by the rings around the outside. So you can see that the strongest colors here are the rings around the ice sheets, which are the temperature thresholds. And basically, this is at 1.5 degrees of warming. The ice sheets dominate because they are plausibly tipped at this low level of warming, and they influence other elements. So they influence each other, and they influence things like the overturning circulation. So they act these triggers, these initializers, kind of keystones that can then go on to tip other elements. Yes. We might also ask, what if our model was missing something? So what if the model didn't have that stabilizing link from the overturning circulation to the ice sheet? This might be because we forgot about it. It might be because it's too difficult to model in our model. It might be because we just didn't know about it. There's, science is always finding new links and behaviors for these tipping points. We're bound to be missing some things. So what happens when we miss one of these stabilizing effects? And I don't think this would be massive news to people, but if you miss one of these elements, one of these links, it completely changes the results. 1.5 degrees in the control setup, the green ice sheet tips about 10% of the time, but if we remove that stabilizing link, it tips almost half the time. And at 4 degrees, without the stabilizing link, it tips all the time because we've gone beyond that threshold, that whole range. But with the stabilizing link, it's able to remain for a bit longer. And so this is a fairly trivial example that if our dynamical system is missing even one bit of dynamics, we can completely change the behavior of the system. And similarly, you might ask, what happens if we were missing a whole dynamical part of the system? So this is if we removed the green ice sheet from the model entirely, so all the links to it, all the behavior of it. So we have our control on the left here. So what this is showing is the fraction of runs in which each element tips. So we've got the green ice sheet down here in blue, which tips about 10% of the time, the Atlantic circulation, which tips about 50% of the time, and then a range of other tipping points. And we might consider, well, what if we run the model as normal, green ice sheet included, run it as we go, but then in our statistics, we just don't include the green ice sheet. So that might be the ideal situation if our model is getting everything right, but we didn't put the green ice sheet in and it doesn't matter. It doesn't affect everything else, but everything else is just fine. The dynamics don't matter. And then you just see it's basically the same, but we haven't put the blue bar in. We haven't counted the green ice sheet. And that's kind of the best case scenario for what our real models might be doing if they're missing this out. And on the right-hand side, you see what the dynamical impact of missing the green ice sheet is, which is that all of the other parts are affected, and you see a big decrease in tipping. And again, this is may seem a slightly trivial example of how these dynamical systems behave, but it's slightly motivated by the fact that our climate models are missing many of these components. So this is again a plot of our network model with crosses over bits that our climate models are either missing or don't represent fully enough to represent these tipping points. So for example, in most current state-of-the-art global climate models, they don't have interactive ice sheets, and certainly ones that are able to show tipping. So we don't have either of these ice sheets in, which is the exact situation we were just showing you with our simple model. In the models that do try and understand these ice sheets that produce the results I showed you earlier, they tend to be one directional. So the climate system and the ocean can influence the ice sheets, but there's no feedback. And so we might have the stabilizing link from the overturning circulation, but we don't have these links back from the ice sheets to the circulation. In many global climate models, the overturning circulation is represented in such a way that it's thought to be overstabilized. Climate models struggle a lot with representing deep convection, this formation of dense water that kind of pulls the currents around. And so when it comes to understanding the dynamics of that circulation, they struggle a lot more. And for other examples, many models don't include an Earth system, so aren't able to represent things like the Amazon rainforest. And certainly many of those that include that struggle to represent dieback and large changes in that system. So we know that our climate models are missing things. We know that in similar dynamical systems, it can have a really big impact. So we need to be careful about interpreting these models in terms of things like tipping points and these dynamical behaviors. So hopefully that's given you some idea of how of the large physical uncertainties we're dealing with and the current methodology we have to try and understand them. And so now I'll talk to you a bit about how we understand the economic damages and how these are commonly taken into the analysis. So the classic traditional way is through damage functions, which basically take a temperature and give you damages as a percentage of GDP. So the classic one, which was used by Nordhaus originally, in a wide range of climate advice, is this blue line here, which takes global temperature change and gives you a percentage loss of GDP. which is, perhaps 5% at 4 degrees, or, a little bit over 10 once you get to 8 degrees of warming, which is a pretty huge level of warming. And this will be based on a range of literature and individual studies that are then collated into these damage functions on this global scale. Damage functions do get a bit more detailed, so they can also be broken down by sector in some cases, so or even by region. So you might notice that in some regions, actually under 2 degrees, they actually seem to benefit from this warming as agriculture can spread out, but actually under 4 degrees, almost everywhere is suffering from that. And these damage functions can be produced in a range of ways. There's kind of two main ways. One is the kind of process-based understanding, where you go sector by sector, you say, okay, I understand the kind of crops farmers are planting, I understand how they might adapt if we warm by 2 degrees, I understand how farmers, in places that are 2 degrees warmer have adapted. So I can kind of predict how that might behave. Or with sea level rise, you can say, I know how much of US GDP is situated within 1 meter of sea level rise of the coast, so I can estimate how much damage that would do. So that's a very common way, but then you have to make a lot of assumptions around how will global trade react? How much will farmers adapt? You can say a lot about if farmers keep the same crop mix, it will do this much damage, or if they adapt, ideally, it will do this much damage. But exactly where you are in that range is hard to say. And then so on and so forth with all the other parts of these. So there's a lot of uncertainties there. The other approach, which I'll talk about a bit more as we go on, is the kind of, I call it like more of a look and see approach. So this is a paper by Burke et al., where they looked at data from pretty much every country in the world over the last 50 years and said, okay, given the range of temperatures they've seen, how has that affected their GDP? So if they had a particularly warm year, how is their GDP affected, and vice versa? And basically fit a load of quadratic regressions through these temperature anomaly versus GDP changes. And what you see is, over plausible levels of warming, perhaps 10 or 20% GDP damages. So about double what we saw in those previous functions. But then with this, you still see issues around, you're looking at relatively small levels of warming with relatively short adaptation times, a few years or decades. Whereas what we want to know is the economic damages when we have much higher levels of warming, which we haven't seen before, and people get a lot longer to adapt. So, again, it's a really useful source of information, but there are still these big uncertainties and potential flaws. It's also important to note that, as I said, this study has much higher levels of damages than those. These are the damage functions I showed you a second ago, but it has this huge uncertainty, and this is partly because we don't know whether countries will respond in exactly the same way. So will one country moving from 18 to 20 degrees respond the same as another one? And also, are the impacts of these temperatures only considered over 1 year, or can they have ongoing impacts? If we have a terrible drought, will that damage agriculture for years to go on? And so in this model, when they considered longer term impacts, that's where you see these much more aggressive damage functions, where at 5 degrees, you're damaging 75% of GDP. So this damage function is much more pessimistic than some of the others we've seen. But really the important takeaway here is just this huge range. There are plausible reasons for damage functions pretty much all the way from 0 or even a slight increase to big damages. So there's this real uncertainty there. And that's kind of where the climate models come in, because often the climate model in these economic assessments is very simplified, and it will often just be a one-to-one mapping between a level of CO2 forcing or a level of greenhouse gas forcing and a level of warming. And that's partly to allow the economic models to optimize systematically in this very predicted way. But we know from climate models, so this is the CMIP6, the most recent ensemble of global climate models, that there's this, multiple degrees, 1 or 2 degrees of uncertainty, depending on which scenario you follow. There's this uncertainty of, even if you know the forcing, you have a degree or 2 of uncertainty. And we know from this that if you're on the worst case, a degree or 2 uncertainty is perhaps 50 or 75% of damages, which is a huge amount, almost everything you care about. But even if you're on some of these lower ones, 3 or 5, between 3 or 5, that kind of 1 or 2 degrees of uncertainty might be the difference between 5 and 10% of GDP, which again is about all the government, would be a big deal to most governments these days. So this physical uncertainty really matters and has a big impact, almost regardless of which of those economic functions you take, and needs to be taken into account in these analyses. That's compounded even further once we look at the overturning, the Atlantic circulation and these tipping points. These climate models, so this is again that CMIP ensemble, disagree on even the current value, between like 24 and 12. Again, you don't need to understand the units in particular, but this is some measure of the rate of overturning, how much water is flowing through. They disagree by a factor of 2 on how strong it is now, but they also disagree a lot on how much it might change between fairly confidently 40–50%, or maybe it's only going to weaken by 5%. And as I mentioned, there's reason to believe that even these aren't fully capturing all the uncertainties. They may be too stable and may not represent this quite right. So we know there's this really significant uncertainty in the physical side. We know that it matters for the economics. And so what we're trying to do is to better characterize this, to bring that into the economic space. So this is a paper by Raphael Kalel and my supervisor David Stainforth at LSE, where they used a very simple climate model, so a one-dimensional chaotic climate model called the Hasselmann model, which can produce these colored trajectories here rather than the very nice, neat black trajectories. And by producing thousands, tens of thousands of these trajectories and putting them through a simple damage function, you can get these ranges of damages, and you can put a price on how much you'd be willing to pay to avoid that uncertainty, how much additional damage that uncertainty will do beyond just that central value of the damages. And that uncertainty is costing you a lot, multiple trillions of dollars in present value, which is, again, huge. It's huge amounts of money. So this is using a very simple climate model to look on a global scale at this uncertainty. And what we're currently hoping to do is to break this down based on regions. So we can take CMIP models. So on the left here, you have predictions from one particular CMIP model, one particular climate model for Indian temperature over the next 100 years or so. And we see a good range of uncertainty there from just these 4 runs. And we can put it through these damage functions to understand how that might affect India. So these damage functions exist for each country. So we can put them through these damage functions, and we can see that with the weaker of those damage functions I showed earlier, we might expect 10% damages for India by 2100, but with an uncertainty range of maybe a few percentage points of GDP on these lower levels. But it's possible that the CMIP models are overconfident, they're not fully exploring this uncertainty space. And if we want to fully explore the uncertainty space, we need a greater number of runs, and we need to ensure that we are actually exploring that full uncertainty range. And so one way of doing that is to create additional runs using models like the Hasselmann model, that one-dimensional model I showed you earlier, to kind of perturb these and give other potential global warming trajectories and use pattern scaling to then predict the regional temperatures. And that can then give us, again, these are very rough in development figures, but that can give us a potential probability range with these hundreds of runs now, again, around both the damages and the temperature, which can help us to better understand the uncertainty here and the potential cost to different regions of this climate uncertainty. This can be furthered to try and understand the impacts of climate tipping points. So with things like AMOC, we can get results like this from climate models, which tell us what the cooling and the warming will be in different parts of the world. And we can join that with projections of temperatures due to climate change and impacts due to climate change, and with trajectories from climate models that show how the AMOC's going to change, how that circulation is going to evolve over time, that I showed you earlier. And we can use that to feed into damage functions and get estimates of the impact of these shutdowns. But as I mentioned, the models are potentially overstabilized. They don't fully explore the range of certainty. They may be representing, in some ways, they may be getting the right answer for the wrong reasons and not necessarily representing all the dynamics correctly of these processes. And so it's important that we include other sources of information in this uncertainty assessment. So that might come from expert elicitations, as we talked about earlier. We can assess, once we have those potential impacts from the models, we can assess what would happen if we applied those impacts on this trajectory or this one that an expert has suggested. Or we can generate additional trajectories from simple models of the overturning circulation, such as the Stommel model or box models like those developed by Richard Wood. And we can generate these other trajectories again to try and explore the full range of potential economic damages and uncertainty due to these processes. So to summarize, I've talked a bit about what tipping points are and the extent we know about them, the extent we know about how they can interact and have that compounding uncertainty. I've talked about how we consider climate damages and tipping points in economic damage assessments and how we put those through damage functions and the great uncertainty there. And then finally, I've talked about how we're bringing this all together, trying to understand the uncertainty in climate tipping points through things like expert elicitation, as well as bringing that physical uncertainty through into the damage assessments and understanding how that range of potential outcomes through the intrinsic climate variability can give really meaningful levels of economic damages that we should be taking into account. So I've really enjoyed talking here. If you do have any questions for me, I will be around after this for a few hours, or feel free to get in contact via these emails or social medias. And if you'd like to read more about the cascading interacting model I was talking about earlier, that's a QR code to the paper, or the name's just down there. So yes, thank you. Any questions? Yes, I don't know if you do as well.
Okay. If we take ones in the room first, and then we can also ask if you have questions online, please feel free to either put your hand up on Zoom or put it in the chat.
Do you want to run them?
Give it a sec to warm up.
10-second hold. All right. Thank you very much. Yeah, that was really interesting. I just had a couple of questions, but the first one I wanted to ask was the cascading model for the work that you do with Nico. You took, obviously you randomly sample from the temperature threshold, and you were saying that the time component is randomly sampled. Is that randomly sampled in terms of when it happens in the model run, or is it like how long this? I was just thinking, because obviously some of the systems have different temporal elements to their tipping, or are all the tipping points just instantaneous?
All the tipping points are a simple kind of fold bifurcation differential equation, and the time scale, they'll have a single time scale, and the time scale is approximately, once you've gone past that threshold, how long they will take to tip. So it's approximately a characteristic time of tipping to go from the off state to the on state, or vice versa. And those timescales are approximately taken from again the Mackay review, but there are questions you can ask around what those timescales should be. So for example, for the ice sheets, the timescales in Mackay et al. Are thousands or tens of thousands of years to fully melt the ice sheets, to fully tip them. But actually for things like the overturning circulation, what you care about is the increased melt. So you don't care that all the ice is gone, you care that it's melting faster, and the timescales for that are much shorter. So there are big questions about what are the timescales? What should these be? Really, the model is a very conceptual model to try and point out some of these high-level conceptual points. Thank you.
Yeah, just pass it over.
Hello. I'm just wondering, when you have these economic suggestions of models of 20%, 30%, 50% GDP being lost, what does that reality look like? I mean, what sectors of economic activity are being lost? I mean, is this some sort of restructuring towards like consumptive patterns being realigned? Are we like living happily as hobbits in a localized economy? Or is this a mark of like rampant destitution or death? Like what? Can you paint a picture?
Well, so I think some of these don't paint a picture at all. So some of these, like these, for example, are they looking to see and they just go, this is what we've seen so far, and we'll just assume that continues. And we've fairly high level, this is how GDP has changed, this is how temperature has changed, and that's it. That's all the information there is there. Some other models, so you can see here, we've got sectors where we're talking about this much due to sea level rise, or these changes to agriculture, so showing expansion of agriculture as we bring in more farmland. And there are ways you can break it down. So with, I recommend this paper, it's a really interesting paper. And they can break it down by country and by region. And you can see that actually in places like Europe and some areas, parts of North America, even at fairly high temperatures, these changes are good. Which means that when you see these really big damages, if Europe's doing kind of okay, if you're getting 50-75% GDP loss, you're looking at pretty catastrophic changes in the rest of the world. So yeah, you're talking mass destitution and death under those very bad scenarios. But a lot of these analyses don't go into a great deal of detail on those because it's so hard to predict these things. How the global trade system will react, how international finance, trade systems, conflict, diplomacy will behave, how different groups will adapt, how much groups will be able to adapt. These things are really hard to predict. So these are often very, very high uncertainty things to just give ballpark estimates of these things. But I will say, but one thing that we're really interested in looking at is a kind of more, it's called like a storylines approach to try and understand what realistically do we think these would look like. So if you're trying to imagine a high impact storyline, what would that look like? What would be happening to people? How would government be behaving? How would these things?
Just in the same way that you have these different models, you could have imaginative models.
Yes, exactly. Exactly. And it's a good way to think around. So there was a long period of time where a lot of these damage functions were limited. I think the original DICE did literally limit off at 20% because 80% of GDP happens indoors. And so they thought it was implausible that climate change would damage anything that was indoors because we can like just do air conditioning or something. Right. But the point there is people do narratives and storylines that are key behind some of these things. And so it's important to have this range of narratives and storylines that we can understand of what assumptions are we putting into these things. What are we doing? That assumption is now gone, by the way. But these are the the questions that I want to understand.
Just we've got a question online, I believe. So if Laurie, you unmute yourself.
Thank you, and thanks, Jonathan, for a great talk. My name's Laurie. I'm a GSI visiting fellow, but also based at the think tank Chatham House. So I spend a lot of time talking with national security decision makers, and of course, the cascading consequences that you just listed off there, the impacts on trade, the behaviour of governments, are the most serious things in many ways that could result from some of these factors. And of course, they're the most decision useful things to consider. Now, we found that sometimes some of those national security personnel, because they are not initiated with climate science and so on and so forth, can be misled by GDP figures into a false sense of security. I don't mean misled on purpose by anyone, that's not what I'm saying, but they misconstrue them. So in the context of what you were just saying about storylines and so on and so forth, what do you think the appropriate use of GDP estimates for things like tipping points are in the context of decision makers who need more of the socioeconomic cascades? It is that's really decision useful, and the risk, of course, that GDP GDP figures might they might misconstrue them. So yeah, what do you think that appropriate use of those kind of estimates are, however more accurate or dealing better with uncertainty would be when briefing decision makers?
I think part of the problem is that these estimates are already out there. We can't take back that these damage functions exist and people can just look them up and have a look at them. So I think we do have a degree of responsibility of trying to give reasonable estimates. And in particular, I think the area that we focus on is really trying to make it clear to policymakers that there is this huge range of uncertainty. So I think a lot of policymakers might look at these nice dotted lines down here from DICE, for example, and say, that's quite comforting. We don't need to worry about this so much. But actually, if you look at this huge uncertainty, which, as we've been discussing here, that's not even taking into account all of the different points that have been raised about different knock-on effects and cascades and uncertainties. If you could choose whether you wanted this much uncertainty or this much uncertainty with these huge bars, you'd be more towards this end. And I think focusing on the specific numbers, I agree, is a real risk. So our focus primarily is on saying, what should you be thinking about, so that we focus on the physical uncertainty, because that's often completely neglected in these analyses. And while factors like the economics and, as you mentioned, the cascading other impacts are really important, and potentially more important, but we can get into that. But the physical uncertainty is critical. We know that physical uncertainty, even without massive climate change at the moment, has big impacts, with all the forest fires or droughts or floods. We know that it's going to matter in the future. And so if it's missing from these models, especially under these really perturbed systems, it can have a big impact. And I think, again, that's why we're looking at the storylines of, we need to get these big changes to the climate and the way the Earth system behaves in a way that is decision relevant for policymakers. So getting the storylines, the narratives of what this might look like, or getting the expert elicitation of, this is the range that we think is plausible. We don't understand enough to give you a specific number, and it would be slightly irresponsible to do, to say we know this number for sure, but we can give you this potential range, and it's likely to be somewhere in that range. And I think we need to be honest with policymakers what we can do and what's reasonable to tell them.
Great, thank you, Laurie. Tim, would you like to go ahead?
Oh, thanks. Yeah, really great talk. Just following up on Laurie, I sort of agree on the GDP being perhaps a narrow focus, but just following up on this discussion, and having been involved in a round table on climate and macroeconomics for a few years with the national academies, I could say that some of these models, these IAM estimates, the small estimates of GDP negative impacts, are basically totally discredited now by people who actually have looked at this properly. And there's lively, if not wild, raging debate going on about the merits and dismerits of the different econometric approaches, which have obviously every approach is going to be limited, but these ones clearly have, some straightforward limitations of you're kind of extrapolating out of the range of past experience into a place you haven't been, and assuming that short-term effects of short-term shocks it could be mapped over to long-term persistent changes, and basically a raft of as usual healthy ongoing debate. But I guess the question is, given all that, can we not, would you say you have formal ways in which we can, shall we say, weight our confidence in some of these very differing estimates, even if they are just expressed in GDP terms? Because right now the financial sector are all over this like a rash as well, and we've written several reports with the Institute and Faculty of Actuaries getting right stuck into this issue, and basically the short version is there's widespread doubts about some of these approaches, and I would just throw them out personally if I'm blunt, but I certainly wouldn't give them equal weighting to a policymaker, let's put it that way, in expressing where the uncertainty is.
No,
So-
I completely agree. I think I hope I gave a good range of caveats
Yeah.
and assumptions that
Yeah,
were in a lot of these damage functions when I introduced them. I think there are certainly some more advanced damage functions coming out more recently from people like Max Kotz or Paul Weidlich, which look at in more
Yeah.
detail, understand these. But I think a lot of them still have the same caveats that you've just described,
Yeah.
and that I introduced earlier. And I think often these are some of our best estimates for the economic damages, but they're often subject to a lot of assumptions that, as you say, may discredit them or make them much less reliable. And I think in terms of what you bring to policymakers, I think it's important to bring a range of approaches, whether you're looking at the kind of looking and seeing kind of approach that we see here of just looking at GDP, looking at temperature, seeing what happens, or the more process-based models. But I think it is also important to be taking approaches like the narratives and storylines that might be less quantitative, but might be more informative in terms of what we can actually do about some of these things and what these changes would look like rather than the raw changes. But I think for groups like the actuaries, I think it is really difficult. I mean, I'm afraid I've only been working on this for 6 months or so, so I don't think I have the silver bullet for to help the actuaries out. I think
the actuaries are okay because the actuaries have a solvency criterion. You need to be solvent against a 1 in 200 year event, so they immediately place themselves in the high end tail of any of these distributions and concentrate their attention there. And I think that's a great strength actually because they're professional risk assessors, and I would argue that's exactly what we should all be doing with the climate challenge. If we accept that some of these tail estimates could be right and we could lose everything basically, because nobody wants to lose everything.
But I think there's a real. I completely agree that I think focusing on the tail risks and understanding those 1 in 200 events is really important. The potential risk of losing everything and having these catastrophic events is really key. But it's also why it's really key that we understand them well, because it's very easy for me to say, look how far down this line goes, it's going to be terrible. But for an actuary, protecting against 75% losses rather than 50% losses is a big difference. And so that you can potentially absorb a lot of capital, a lot of money that could go to other causes, which you can risk locking up in this one with the high level of uncertainty we have. So it's a really difficult balance, I think.
Absolutely. Brilliant. Yeah.
Thanks, Tim.
Great, thanks, Tim. I think that's all we have time for today. So should we thank you again? Thank you for coming, everybody.
Thank you very much. Brilliant.